Oh, hi, this is lecture number 36 on management of salt affected soils. So, basically I am planning for two lectures. In the lecture number 1, mostly we are going to learn some terminologies on what is salt affected lands, and then how do you estimate the leaching fraction. Okay. So, then and how to calculate the salt stress coefficient, similarly the water stress coefficient, and then the combined salt and water stress coefficients here in this. In the next lecture, we are going to see some of the examples of these, and then the sodic soils and other things. Okay. So, if you see these salt affected soils around the world, so basically what is the salinity? So, salinity refers to the amount of soluble salts present in the soil. So, soluble salts could be sodium salt, potassium salt, calcium. So, there are several salts which are present inside, and magnesium salt, all those things, right. So, the soluble salts which are present in the soil, it is represented as salinity, and whereas sodicity exclusively for sodium salt which is present in the soil. So, that is referred to sodicity. So, around the world there are 80 million hectare of lands are being affected with salinity. So, at every minute, if you see, around 3 hectare of land is being affected with or converted into saline soil. So, it is converting the fertile soils in faster rate, around 3 hectare per minute. So, and world area of saline and sodic soils, if you see, so around the saline soils are 434 million hectare, and whereas the sodic, the other way, the saline soils around 394 and sodic soils around 434 million hectares. Okay. And the extent and distribution of salt affected soils in India is 6.7 million hectare, right. So, if you see this Indian map, so the black things, wherever the black strips, so these lands are affected with salinity. Okay. So, these patches, so here and here, so where the black spots all are showing the affected lands in India. Okay. So, then what are the salinity units? So, how do measure the salinity, soil salinity or water salinity? So, here the units are measured in electrical conductivity units or EC. So, and we, in order to how to measure the electrical conductivity. So, there is electrical conductivity meter. So, that we have discussed earlier in the previous classes. So, using that meter we are going to measure electrical conductivity. So, generally the units of electrical conductivity are decisiemens per meter or ds per m and or millimos per centimeter. So, the total salinity of irrigation water. So, in order to convert this EC, so the knowing the electrical conductivity of particular water or irrigation water, you can convert that into concentration of salts. So, that is CIW, that is measured in concentration, is generally measured in ppm or milligram per liter. So, if you can multiply with 650 with electrical conductivity, so you can get the value in concentration. Okay. So, then the 640 may vary with region to region. So, I mean roughly you can use, but in order to adjust this you have to do some kind of the trials. Okay. So, where in this equation where ECIW is the electrical conductivity of irrigation water, decisiemens per meter, and standard measurement for soil salinity is expressed as saturated paste extract. So, that is ECE. Okay. So, here the two things. So, salinity of soil, right, ECE and salinity of water, so that is ECIW. Okay, so two things here. So, salinity of ECIW, salinity of water, this is easy. So, you get the water and put the electric conductivity meter, and you get the meter reading in deci per meter. So, whereas for soil, because this is a solid material, so what you have to do, you have to extract the solutes from the soil by adding water and by saturating it completely and making it slurry, right. So, then after that you have to extract water out of that paste, right, and then the dissolved water, I mean the water will be used to measure the soil salinity. Okay. So, here that is why it is called soil salinity, which is expressed as saturated paste extract salinity. Okay, saturated paste extract. So, you get a soil this which is the solid material, and you add DI water, right, add DI water and then make it a paste. Okay. So, then leave it for one day, the next day if you come and filter it, so then the water which is coming out from the filter will be used to analyze the electrical conductivity. Okay. So, that is why that is equivalent. So, saturated paste extract equivalent. Okay. So, then so next is what is osmotic potential, because when you are talking about salinity, so the potential which is related to salinity is osmotic potential. Okay. So, because of this, the water extraction by plants is limited. Okay. So, if you see this, so water with higher concentration of salts has lower energy, like that means the more negative, I mean more suction. So, it will have more suction or induces more suction. So, then water with lower solute concentrations. So, as you see, so if you have this is a beaker with semi permeable layer in between, and you have a salt water and you have a fresh water, right, this is a fresh water. So, after equilibrium, if you observe, right, so the fresh water level goes down, whereas salt water level goes up. Okay. So, that is really so that means the salt water is not allowing water furthermore. Okay. So, there is a transportation of salts and the fresh water going here and there, but what happened after the equilibrium, you can clearly see the water, right, which is going into the saline water, and saline water level will be increased, and there is a gap between the initial and final, and this really creates this suction. Okay, suction. So, extra suction in the soil. Okay. So, that means if you have a plant here, and there is a saline water, right, this is a saline water. So, the water which is present around, so that will be pulled towards the salt water and creating suction to the plant. Okay, the same thing. So, water is driven towards higher salinity region, and therefore, the plant has difficulty to pulling water from high saline soils. So, because of that, the more suction will be created the root zone. So, the osmotic potential energy is saturated soils. So, this equation will be used once you have the value of the soil salinity, right, electric conductivity as I explained before the previous slide. So, using that, if you can multiply with 3.6, you can get osmotic potential, right. So, that is minus 3.6, right. So, then where ECE is the electrical conductivity of saturated paste extract, that is deci per meter, and psi naught is the osmotic potential in meter. Okay. So, this is a simple equation converting the electrical conductivity of the soil into osmotic potential. So, at the dry soils, the salinity increases, of course. So, initially if the water is saturated, keep on drying the soil. So, the salinity is going to increase. Okay. The osmotic potential is a function of water content. So, since using this theory, so if you can also put the water content values here, I mean append to the equation. So, then in that case minus 3.6 into ECE, right, the same equation here, and multiplied by theta S by theta. So, where theta S is the saturated moisture content and theta is the current moisture content. So, this is the less than, so theta is less than theta S. Okay. So, in that case, so anyway, it's a volume basis, so both. So, that means, so the salinity, increases. So, because when theta is less than theta S, so if you decrease further, so psi naught is going to increase. Okay. So, that means negative term is going to increase. So, negativity increases means more suction is going to be created. So, here the simple example, calculate the osmotic potential in the soil at 25% water content and ECE, which is the soil extracted electroconductivity 1, and then water content is 50%. So, since so here we can plug this easily, right, and so at 25% water content, right. So, theta S, so osmotic potential in the soil at 25% moisture content is ECE, which is 1 ds by m, and water content is 50%. So, 50 by 25, so 50 by 25 basically. So, this is not 100 by 50. So, this is, so theta S here, the water content is 50%. You calculate the osmotic potential in the soil at 25% water content. So, here this is 50 and this is 25. Okay. So, net result anyway it will not change. Okay. So, then you get psi naught is equal to minus 0.72 atmospheres, okay, minus 0.72 atmospheres. So, because 1 atmosphere is equal to 10 meter, right. So, the next is salinity stress coefficient. So, since just similar to your crop coefficient, you have salinity stress coefficient and water stress coefficient. Okay. So, here let us see the salinity stress coefficient. So, what exactly salinity stress coefficient? So, here the increasing soil salinity decreases the water uptake, as I mentioned before. So, thus decrease the yield. So, once the plant is not able to extract or pull water from the soil, so that is going to show the plant water stress, right, that definitely influence the yield. So, that results in reduction in yield. So, in this graph if you see, so this is salinity levels, right, saturated paste extract of salinity, soil salinity is on x axis, and the relative yield, which is actual yield by the maximum yield, right, the relative yield. If you see this graph, right, so as salinity increases, right, so the relative yield is going to be almost constant at this region for certain salinity. Then after that the salinity effect is going to influence on the yield. So, at this point if you see, the salinity is constant. So, the yield is constant. So, that means salinity up to some level is not going to influence on yield, and we call this is threshold salinity. So, if you see this from this graph, especially this is a example of cotton, response of cotton to increase the saturated paste extract salinity. So, here if you see this number from this graph, it is showing like 7.7. So, that means from the figure, so EC exceeds 7.7, the yield begins to decrease. Okay. So, up to 7.7 the yield is not going to be affected with salinity. So, the crops that are classified as sensitive and moderately sensitive and moderately tolerant and tolerant to salinity have no reduction yield at ECE 1, 3, 6 and 9.5 decisemen per meter. So, similar to here as we see, so up to certain salinity level the yield is not going to increase. So, here So, based on that concept, the crops are classified, right. So, because the crop is I mean the response of this particular thresholds are different with plant to plant or crop to crop. So, having that in mind, so the complete the crops are classified as sensitive crops. So, the sensitive crops generally up to 1.0 ECE. So, yield is not going to decrease. In case of moderately sensitive crops, so up to 3 decisemon per meter of soil salinity, the yield is not going to decrease. So, and up to 6 decisemon per meter in case of moderately tolerant crops. So, the yield is not going to decrease, and up to 9.5 decisemon per meter the tolerant to salinity. So, this is called the crops tolerant to salinity, 9.5 decisemon per meter. Okay. So, the next is so for example, vegetable crops are generally sensitive to moderately sensitive to salinity. Okay. So, I mean vegetable crops are in categorized in between sensitive to moderately sensitive. Okay. So, this in between. So, field crops such as cotton, wheat, barley tend to be less sensitive to salinity, and this natural resources conservation services classifies the irrigation salinity levels as no restriction on use, right. This is based on the irrigation water. The previous thing is based on the soil salinity. Now, this is based on the irrigation water, the salinity of irrigation water. So, the irrigation water which has electrical conductivity less than 0.7, right, can be used, no restriction so on use. So, you can use for any crop, and slight to moderate restriction generally 0.7 to less than 3, right. So, and severe restriction, so the ECIW which is less than 3, it is severe, no it is not less than, it is greater than 3, right. So, greater than 3 is careful, very careful, this is severely restricted, we should not use it for irrigation. Okay. Okay, so, salinity stress coefficient is denoted with Ks salt, right, salinity stress coefficient. So, which is expressed as 1 minus B divided by 100 into Ky ECE minus ECET. So, here ECE which is a soil salinity, ECET. So, this is a threshold soil salinity, the threshold in the sense beyond that level the crop yield is going to reduce. Okay. So, start showing the reduction in yield. So, if suppose your soil salinity is less than the threshold, so then the stress coefficient, the saline stress coefficient is 1, because that is not going to influence the yield. So, if it is ECE is greater than ECE, if it is greater than ECET, right. So, we are going to use this equation. So, this equation says this is 1 minus, so B is the slope of this the curve, right, B is the slope, and ECE and ECET we know very well, and Ky is the coefficient. So, Ky is the crop sensitive to water stress. So, we are going to improve, I mean we are going to put the crop water stress coefficient here Ky. Okay, Ky is the crop sensitive to water stress. We have some table values, we can directly use Ky value for particular crop. Okay. So, then as I mentioned the water stress coefficient. So, as the salinity stress, the water stress coefficient is generally calculated under the assumption that yield decreases linearly with the increased percentage of water depletion. So, similar to your I mean salinity stress, the water stress coefficient, so that directly influences the amount of water which is less when compared to the field capacity, right, or available water, if you see. So, the threshold percentage of depletion theta t, right, this is threshold similar to your salt. So, up to certain water content, see the crop does not show any yield reduction. So, but there is a threshold water level. So, beyond that it is going to show the reduction in yield. So, for example, if you remember the management allowable depletion, that is MAD. So, this is similar to that. So, is the water content in which yield starts to decrease. Okay. So, the way Ks water decrease linearly from 1 to linear from 1 at theta t to 0 at theta wilting point. Okay. So, here, so that means theta field capacity. Okay. So, then theta t and then theta w PWP. So, that means, so between theta FC and T, so the plant does not show any yield reduction. Okay. So, this you get maximum yield E max. Then after that theta T and theta W, so you get actual yield, and here the yield is going to be declined, maybe you get 0 yield. Okay. At theta WP. So, using that concept, so the Ks water which is equal to theta minus theta, this is wilting point, by theta threshold minus theta wilting point. So, this is actual water, right, actual water. So, from here, so theta t which is equal to theta f c minus p by 100 in theta f c minus theta w p. So, the same equation, if you can convert that into theta t, right. So, this will go the other side, and then p is basically the point at which yield decrease in contrast to MAD. Okay. This is kind of a threshold point at which the yield is going to decline, which may be equal to P or less than P. Okay. So, P, so whatever the yield we are getting, so which is the yield decrease in contrast to MAD, which may be equal to P or so less than P. Okay. So, water stress coefficient, so combination both water as well as salt stress coefficients. So, the combined water and salt stress coefficient Ks, so that is equal to Ks salt multiplied by Ks water. Okay. So, Ks salt, Ks water, we have already got the equations in the previous slides. So, if you can get both and multiply that, you get Ks, that is a water stress salt and water stress coefficient. And the relation between yield decrease and combined stress, which is equal to 1 minus actual yield by maximum yield minus the Ky, which is the called the crop sensitive to water stress, okay, and 1 minus Ks. Good. So, and here this is showing the Ks versus water content curve. So, percentage depletion and Ks. Okay. So, if you see this, theta t is the total threshold t. So, for certain depletion, right. So, this is not showing, this is the field capacity and theta t and theta WP. So, the yield is the Ks or the stress is almost constant, this 1, right. So, then after that, so at this depletion level, up to this depletion, the Ks is 1, but after that the plant is showing moderately drought tolerant crop, right. So, it is going to show the effect of the stress. Okay. Similarly, there is other classification of crops and other classification of crops. The p values are given 25% and for 50%, right, and this is in between, okay, 40%, something like that. Okay. So, now from equation, the previous equation, you can rearrange to solve the actual yield. So, y a, so this one, so y a is equal to 1 minus k y into 1 minus k s into y max. So, here the crop sensitive water stress, the k y values, are given for different the crops. So, you can adopt from this table and substitute it and get the actual yield. So, here there is an example. So, they calculate the actual yield for cotton for a growing season. If average salinity during the growing season is 10.4 decicement per meter and the average water content is 14%, theta Fc, that is field capacity, is 20%, wilting point 10%, and Ky, right, 0.85, and maximum yield 1285 kg per hectare, and MAD 50%, threshold 7.77 decicement per meter, and B, that is the slope, which is equal to 5.2. So, this is the direct problem, direct problem. If you know the equation, you can put the values. So, first of all, the theta T, right, theta T is the threshold moisture content for which the yield is almost constant. So, beyond that yield, the crop shows yield reduction. So, that is theta Fc minus MAD by 100. So, previous and theta Fc minus theta Wp. So, okay. So, from the given values, theta T, which is equal to 20, okay, minus 0.5 by 100. So, 20 minus 10 is equal to 15% is the theta T. So, that means the field capacity 20% and 15% and 10% is a wilting point. So, during this 20 to 15% no yield reduction observed, then beyond that the yield is going to reduce. Okay. Now, Ks water. So, the equation, you get the equation theta minus theta Wp, theta T minus. So, put all values and you get 0.8. Now, this is water stress coefficient and this is salt stress coefficient, and bring the equation here, 1 minus B by 100 into Ky into ECE minus ECET. So, the values are given and put all the values, you get Ks salt is 0.83. Now, knowing these two stress, you can get the combined salt and water stress. So, this is a Ks combined salt and water stress is equal to water stress coefficient and salt stress coefficient, that is 0.67, and you can calculate the yield by knowing the equation, right, Ya actual yield, that is 1 minus 0.85 from the table for this particular crop, the Ky value, and 1 minus so this, and then the maximum yield, and you get 924 kg per hectare. So, look at this. So, this is the maximum yield, and due to both water stress and both combined stress, the yield is reduced to 924 kg per hectare. So, that is the effect of the salt and water stress. So, then another example, if you see the calculate the yield reduction for sugar beets. So, assume 80 centimeter is applied and 100 centimeter is required, right. So, 100 centimeter is required, but you only applied 80 centimeter, right, and Y max is 40 tons per hectare. So, this is the direct formula. So, get the direct formula here and see what values are given. Ky you can get it from the table for sugar beets, and 1 minus. So, here the Ks, the Ks also can be written as, so in terms of water, that is ETC, that is adjusted divided by ETC, right, crop evapotranspiration and crop evapotranspiration adjusted. So, this is due to your stresses. Okay. So, putting the values, so ETC adjusted will be 80, right. So, that is 80 centimeter is applied, right, and 100 is actually required, 100 is required, but 80 centimeter only you applied. So, that means there is a stress. So, and Y max is given, you put the values, and finally, the yield reduction 32 tons per hectare, that is actual yield. Okay, so, the other one is salt balance at farm level. If you see the salt balance, so this is simple mass balance equation, right. So, this is the field, and there are some inputs, right, and their output. So, what are the inputs? Inputs are here basically the water, right, and salts present in water and salts present in soil, right. So, here the water inputs could be irrigation water, right, and rainfall water. Okay. And here from groundwater, this could be a groundwater, and the corresponding salinity levels. Okay. So, here the salinity, if you see Ci and Cr, and this is Cg, groundwater, right, groundwater, and the outputs could be here drainage, basically drainage. So, the drainage could be surface drainage and subsurface drainage. Okay. So, surface drainage, let us say surface drainage SD, and let us say subsurface drainage D. Okay. And then there is a plant uptake. Okay. So, that is a plant uptake, let us say P. Okay. So, these are knowing the volume of water at each level and the corresponding concentration, and you can really balance the salt levels. So, what other inputs? Other inputs could be like the practices, you put fertilizer or anything. So, that also contains some salts, the salts. So, that is also the input. For example, here like mass of salts in agriculture, like Ma, this is up due to application of fertilizers. And then the other inputs are like the dissolved salts, I mean salts dissolved from the soil minerals. So, which is present inside the soil minerals. So, that is also input, that is Ms. Okay. Then Mp, mass of salts precipitated. So, the salts which are precipitated, sometimes what happens, the salts are if it is saline water. So, then due to a lot of evaporation, the salts are accumulated on top, right. So, that is rest on top. So, that is also, that is Mp, there is also left, okay, output kind of thing. So, putting everything, you get a delta MSW, which is I mean this is a change in the salt storage. Okay. So, with this the equation here, as I said, VICI for irrigation. So, volume, right. So, meter cube multiplied by kg per meter cube. Okay. So, this is concentration, it gets cancelled and you get the kg, because since this is water, right, you multiply with the density. Okay. So, then Vi into Ci, Vr into Cr, this is due to rainfall, this is due to irrigation, and due to groundwater. This is all inputs, and Ms is the soil minerals, I mean salts due to soil minerals, and Ma is the fertilizer application or agricultural inputs application, right. So, this is all inputs, and then the outputs. Outputs are like this is the drainage, and this is surface drainage, and this is due to crop water uptake, and then Mp, which is precipitation kind of thing. Okay. So, finally, you get that is a change, right, the change in salts present in the soil. So, if it is a steady state, for the steady state, so Hillel 1998, so what he assumed, so for salinity concentration during season and the year, that is constant. So, that means that there is no change, and in situ precipitation liquid to solid and dissolution solid to liquid of salt is negligible, that means Ms, Mp, Ma all are 0, right, and crops removed a negligible amount of salt, that is Mc is equal to 0, sorry, this is Mc. Okay. So, and this is and then finally, if you put the values VICI, VRCR, which is equal to Vd minus Vg into Cd. Okay. So, if C in is the average weighted salinity of in both the cases Vi and Vr. So, if C in is the average weighted salts present in irrigation and rainfall, okay, of the precipitation, irrigation, water, and Vg is negligible, right. So, there is a less inflow or upward water or capillary water from water table to the root zone. So, then the equation can be written in this way: V in C in, which is the C in is the average concentration of salts of irrigation and rainfall, and V in is the volume of inflow, and V out C out, right. So, because this is negligible, So, V d is simply the drainage. Okay. So, drainage outflow, and the the concentration, or you can convert volume into depth units, right, d in, because the form is same in both the cases. So, d in is the depth units, d in, c in, d out, c out. So, then the leaching now, what is the leaching fraction? So, leaching fraction LF is denoted with LF is the leaching depth or CPS depth divided by the applied depth, where I in the following includes precipitation as well as irrigation. Okay. If C in is the average salinity in both irrigation and precipitation. Okay. So, leaching fraction, the amount of water which is being used to leach the salts from the soil body, you can say. So, leaching fraction is equal to d out, drainage out, minus the in, right, depth in. So, basically d out is the CPS and in is the irrigation as well as rainfall, this is the total. Okay. So, since d in C in is equal to d out C out in case of steady state salt balance equation, the previously is explained. So, now you can put the values, I mean this here. So, d in C in, which is equal to, so d out. So, here from here d out is equal to, or d CPS is equal to LF into d in. So, put the values here in place of d out. So, LF into d in is the I. So, this is what d out. So, the finally from this equation C out is equal to C in, right, C in divided by L out as LF, right. So, d in is I, right, d in is I and here is I gets cancels out. So, finally, C out is equal to C in by LF. So, because Ce is proportional to the concentrations C, right, in order to get the salt concentration, knowing the EC value, right. So, that is what 640 into EC, which is equal to your concentration in ppm, right. So, since it is proportional, the leachate salinity for uniform water application can be written as, now you convert that into EC units. So, EC dW, that is the drainage water, EC in minus LF. Okay. So, then and the same thing now, if you look at this, the depth of drainage water is equal to the irrigation water minus DET. So, here D out, which is equal to in minus DET. So, depth of water which is under evapotranspiration and the amount of water is being applied. So, that will be equal to D out. Okay. So, get the LF equation, LF equal to D out by D in, right. So, then with this you get LF is equal to I minus DET, this is DET, okay, by I. So, this is leaching fraction in terms of water depths. Okay. This is a water depth. Knowing the water depths, you can get leaching fraction, but similarly there is an empirical equation, right, empirical equation knowing the salt content or salt concentration or electrical conductivity of both irrigation water and soil. So, knowing the those values, LF also can be estimated by EC IW, that is electrical conductivity of irrigation water divided by 5 times EC of soil minus EC of water. So, this is an empirical equation and mostly is considered as a standard equation in order to find out or in order to estimate the leaching fraction. Okay. So, I think with this this is the end of the lecture. So, in this lecture basically we focused what is salinity and how it is being measured and what are the units and what is the osmotic potential and how do you estimate osmotic potential, and then what is the soil stress coefficient, what is water stress coefficient, and how do you get the combined soil stress and water stress coefficient, and how to estimate the yield reduction due to soil stress and water stress coefficients. Okay. And finally, what is the salt balance equation, and what is the steady state salt balance equation, right, and finally leachate fraction, and how to estimate the leaching fraction knowing the inflows and outflows as well as their concentrations, right. Thank you.